This is question 20 from the third CSAT sample paper. In this question we were asked, how many ways can we order the numbers 1 to n so that no 2 out of 1, 2 and 3 are next to each other? And we do this in the cases where n equals 5, n equals 6, and then generally for n greater than 4. I just want to note, in the question itself they phrase it as how many permutations are there of these numbers, but a permutation is just a reordering, so it's the same as asking how many orders are there. So if you want to have a go at this question yourself, pause the video now. Okay, so let's start with n equals 5, as they say. And if we've got the numbers 1 to 5 and we want 1, 2 and 3 not to be next to each other, what can it look like? Well, imagine we put the numbers 1, 2 and 3 down. I'll put them in this order. Then we need them to be separated by some other numbers, and there's only 2 numbers left, which are 4 and 5. So we've got to put 4 and 5 in these spaces in some order. Also, I put 1, 2 and 3 in this order, but they could be in any order themselves, as long as there are gaps in between. So that means that we have, how many ways of reordering these? Well, 3 factorial. And then how many ways of putting 4 and 5 in these? That's just a number of ways of ordering 2 things, that's 2 factorial. And then what's the total number of orders? Well, my choice for this, for ordering these 2 things, is independent of my choice for ordering these 2 things, so I just multiply. So I get 3 factorial times 2 factorial, and if we want to whether that's a number, well, this is 6 times 2, so that's equal to 12. Okay, so now let's have a go at n equals 6. So if we just think about adding a 6th number here, the issue is that when there were 5, we knew there had to be 1 in each of these spaces. When there's 6, there's multiple places we could put the 6th one. So we could put it in here or in here. We could also put it at the ends, as long as there's at least 1 number separating 1 and 2 and 1 separating 2 and 3. So that means we have multiple places to put the extra gap. So what are we asking ourselves? We're asking, where are the gaps? So this 6th gap, which of these places are it going to be? And then how many ways can we fill them? Which is what we asked when we found this number. Well, let's draw all the possible places we can put the gap. So we can put it here, here, at the front or at the end. That's 4 different cases. But in each of these cases, the same thing happens. So I've written 1, 2 and 3. Obviously, we can reorder those. Also, once I've got these gaps, I can put 4, 5 and 6 in them in any order. So that means we again have 3 factorial ways to order 1, 2 and 3. And now, because there's 3 extra numbers, there's going to be 3 factorial ways of ordering them. And then there's 4 different cases, and which case I choose is independent of these numbers. It doesn't affect these numbers. So we just got another, well, basically we multiply our choices by 4, because we've got 3 factorial times 3 factorial choices in each of these cases. So that means our total number of ways is 4 times 3 factorial times 3 factorial. And if you want to work this out, well, this is 6 squared, which is 36, times by 4, and you get 144. Okay, so now we've tried this, let's think about the general case where n is greater than 4. Okay, so let's just talk about the method we were using before. What we did was we put down 1, 2 and 3. We know we can reorder those afterwards. Then we placed gaps around them and we tried to place the other numbers in those gaps. So first we place the gaps around these numbers, and then we count how many ways the other numbers can be placed into those gaps. So let's do that visually. So we've got 1, 2 and 3. We know there has to be a gap in between each of these. So there has to be at least 1 gap in these places. But now n can be 5, 6, 7, up to whatever you like. So we're going to have a bunch of extra numbers. We have to put 2 numbers in these spaces, but we've got a bunch left over. So we can imagine adding extra gaps around here, but they could be in any of these 4 places, as we discussed before. So we can add any number of gaps in these places, essentially, until we have, well, how many gaps are we allowed? We've got the numbers 1 to 3, and then however many numbers are left, that's how many gaps we need. So let's count how many things there are that we need to take into account. So we've got n numbers, and n minus 3 of them are not 1 to 3, so that means we need n minus 3 gaps. And 2 of these gaps are already accounted for, So that means we've got n minus 5 extra gaps which go in any of these 4 places. But once we get to these green ones, the ones that don't have to go in any particular location, well, we have completely free choice, and we've got 4 choices each time. So for each of these extra gaps, we can put it in any of 4 places, and it doesn't affect any of the others. It's not affected by what we've chosen before. So that means there's just going to be 4 to the power of n minus 5 choices. 4 for the first one, 4 for the second one, etc. We multiply all those together. So just to note, something I'm using here is that I'm placing gaps at the moment. I'm not actually placing the numbers in them yet, and that means they're all the same. So if you imagine back to when we did this for n equals 6, we just had spaces and then we put the numbers in afterwards. And if I swap 2 of those spaces, it doesn't change the pattern of gaps. So that means the order doesn't matter. It's only the position with respect to the fixed numbers. Because if the order mattered, then I'd have to take into account how many ways I can permute the gaps, but they're all the same, so it doesn't matter. Okay, with that in mind, now we've got the number of gaps, we just need to think about how many ways we can place the numbers in them. Well, firstly we've got these 3 numbers we can permute, so that's 3 factorial. And then we've got n minus 3 left, and we can put them in any order. Now we've decided where the gaps are. So that's n minus 3 factorial ways we can order those. And then these 3 things are all independent. So we can just multiply them together. So that means the total is 4 to the n minus 5 times 3 factorial times n minus 3 factorial. So if you wanted, you could rewrite this. You could turn this into a 6. You could turn this into 2 to the n minus 10. But this is as simple as anything else you're going to get, so we'll leave our answer here.